We are live. Okay. Hello everyone, welcome to third live session for this course, Fundamentals of Bioprocess Engineering. So if you have any query, please text in this chat box. So for time being, we have received a couple of queries. So that is mostly related with the pattern of the final exam. So pattern of final exam, if you see this NPTEL MOOCs website, so it says this, what is the fraction from the assignment? The 25% from the assignment, right? And 25% from the learning, right? So what you have to do, you have to revise the assignment part. So that will help because many questions will be there from the similar to the assignment questions. In addition to that, from the lecture slide also, you need to see there will be, based on the, that is called the recall, that will have about 35%. So if you see from the lecture slide, so you will have 35% questions. And from the assignment, you are going to have 25% questions. And again, 25% question, there will be similar, which is there in the assignment. So I suggest to emphasize more on the assignment questions. And further, based on the concept, there will be 15%, so that is called the open questions. So this is the distribution. Assignment will be 50%, recall mostly from the video lectures, 35%, and open questions based on the concept, that will be 15%. Is there any other queries? Only two queries, right? Syllabus, yes, syllabus, that is important because if you see that any bioprocess engineering course, so this course covers most of the key concept. So every week have certain weightage. So if you are not comfortable with a particular week, that's okay. But whatever week you are comfortable, you should be very much thorough with it, so that you should be able to answer those assignment part and this question from the video. And if possible, you can attempt this open questions. And in addition to that all the questions will be MCQ based. We are not going to have the subjective or descriptive questions. So all will be MCQ based, and you will be having 4 options. You have to choose the correct one. But of course, there may be numerical questions that you may need to use the scientific calculator that will be provided during your online exam. The exam for this course will be in online mode, not in offline mode. Now going ahead, what we can do, we can wait if there are some more query coming, and parallelly we can proceed with this tutorial questions of week 9, 10 and 11. So week 9, it was related with heat transfer in bioprocess, and also one last lecture was from the scale. So there we discuss what are the heat transfer mechanisms in the bioprocess, how heat transfer takes place, and what is the kinetics of thermal healing. Or you can say cell-based kinetics, and mostly it follows the first order kinetics. Then when you go for sterilization, and there could be two modes. One is batch and another is the continuous sterilization. In the case of batch sterilization, there are typically 3 steps: heating, holding, and cooling steps. Holding time is about 20 minutes at 121 degrees centigrade, while the continuous sterilization is high temperature and short waiting time or the short time. So in the case of continuous sterilization, this 121 degrees centigrade is increased to about 140 degrees centigrade, so that the holding time decreases to 1 to 3 minutes. Then we discuss heat transfer equipment, particularly this double pipe heat exchanger and shell and tube heat exchanger. So whatever configuration it may be, one side there will be cold fluid, other side there will be hot fluid, and through which the heat transfer will take place. And in bioprocess scale-up, this is important criteria, because once you have developed something in laboratory, that need to be tested at pilot scale and finally at the production scale. So there we discuss there should be certain criteria to maintain the certain similarity of key parameter like power per unit volume, or the constant tip speed, constant Reynolds number. So these are the dynamic parameter. In addition, there could be one geometrical similarity as well. For example, constant height to diameter ratio. Going ahead with assignment questions. The first question was, which of the following sterilization technique is used to achieve faster killing of contaminating microbes without degrading the nutrients? So the option is high temperature and short time, HT, ST, and this is the same we apply for the, particularly for the continuous sterilization. So there is another advantage of this process, because if there are heat sensitive nutrients in the media, so they are also not exposed for the longer duration. So we can work with media containing some sensitive nutrients like proteins. Second question was this: what is the death rate constant of a sterilization process in which probability of extension is 0.85? So if you remember the probability of extension, it is defined as 1 minus the probability of live cells, or probability of the cell which are alive. Further, in this question, the initial number of cells N0 is not given here. So what we can see, we can think of capital PT. Capital PT has 1 minus small pt, small pe. So, and the small p will be e to the power minus kd into t. So small pt will be 1 minus capital PT. 1 minus capital PT, it will be 1 minus 0.85 equals 0.15. It becomes ln 0.15 upon t. So we'll get the value of Kd as 0.0948 minute inverse. So option B is correct here. Going ahead for the question number 3, it says an experiment is performed to study the toxicity of chitosan loaded silver nanoparticle against Mg63 cell line. The media used for this mammalian culture is DMEM with 10% FBS. So once FBS is there, this is considered to be a heat sensitive nutrient such as proteins, growth factor, and hormones for optimal growth and purification. So for such cases, what kind of sterilization technique will be used to kill the contaminating microbes at the same time to avoid thermal degradation or any kind of degradation of nutrient? So as I told, in this case, of course, we cannot go with thermal sterilization. So the most suitable option for the sterilizing the mammalian cell media, mammalian cell culture media is filter sterilization. Next question is this. It is related with the air sterilization. It says interception mechanism will occur when particle in the air process. So if you remember this sterilization of air, we cannot go with thermal sterilization because of poor conductive nature of air. So we go with filter sterilization. Typically we go with the Dept filter. So if you see the mechanism of Dept filter, so it is inertial impaction, interception, diffusion, and the last one is electrostatic attraction. So first one is inertial impaction. It is based on the mass and size, but interception is purely based on the size. So the correct option will be no mass per particle size. And the third one is diffusion. So material particle diffuses inside the filter depth, and last one is electrostatic attraction. If your particle is oppositely charged to the filter medium. So this is interception. This is mechanism is considered where the particle has size but no mass. Next question was fermentation media is cooled from 121 degrees centigrade to 23 degrees centigrade in a double pipe heat exchanger. If cold water is flowing in a counter current direction and is heated from 20 to 83 degrees centigrade, what is the log mean temperature difference? Yeah, so this part we have discussed. So this first we have to see what is the flowing pattern. So this is a counter current. Counter current means the inlet of hot stream will be outlet of cold stream. So if you see the temperature profile, it is the hot stream is temperature is decreased from 121 to 23. At the same time, this cold stream is heated from 20 to 83 degrees centigrade. So in the case of counter current, this 121 will be at the inlet, and this 20 degrees centigrade, rather this 83 degrees centigrade, its outlet will be at the inlet. So how we calculate LMTD? We calculate LMTD as delta T2 upon delta T1 divided by ln delta T2 upon delta T1. It can be T1 minus T2 or T2 minus T1, both will get the same answer. So what we are getting, hot fluid is coming from 121 to 23 and cold fluid is heated from 20 to 83. So delta T1, if you consider this point delta T1, it will be 121 minus 83. So this will be 38 degrees centigrade. And if I see delta T2, so this is going outward one side and this will be going exiting at other side at the same side. So it will be 23 minus 20 will be 3. So in this way you can calculate LMTD and you are getting log mean temperature difference as 13.78. And this delta T will be used to calculate the rate of heat transfer. Next question, what is the decimal reduction time of microbe having the thermal death rate constant of 1 minute per inverse? So KD value is given, it says it follows the first order. In the case of first order, decimal reduction time means NT is 0.1 of 1. Or you can say if N naught is 100, then NT will be 10. So it is a 10 time reduction. In that case, if you see the formula, it says ln NT upon N naught equals minus KD into T. So in this case again, NT upon N naught, or if you can reverse it, it will be ln N naught upon NT. So this will be ln 10 equals KD into T. So ln 10 means 2.303 divided by KD. So that will be the time. KD is 1. So your answer will be 2.303 upon 1. So it says decimal reduction time is ln 10 upon KD or 2.303 upon KD. You will get 2.303 minute. Next question was, an evaporator is insulated using glass wool material of 0.27 millimeter thickness. The innermost surface and outermost surface of the insulation are at two different temperatures, that is 850 and 295 degrees centigrade. Mean thermal conductivity of glass wool under this condition is 0.21 watt per meter per Kelvin, and rate of heat loss is through 2 meter of evaporation surface wall. We need to find out. So area is given as 2 meter square. So first you need to understand what will be the mode of heat transfer here. So the mode of heat transfer here will be the conduction, because thermal conductivity is there, area is there. So how do we calculate the heat loss? Our rate of heat transfer is Ka delta T upon delta X, the temperature gradient. Thermal conductivity is given to you, area is given. What will be delta T? Delta T will be 850 minus 295 divided by dx. What is the thickness? 0.27. So that's it. You get the value of rate of heat loss, and the correct option is option C. The next question was, a pilot sterilization was conducted in a vessel containing 150 meter cube of medium, and N naught, initial number of spore was 10 to the power 5. After sterilization, the allowed level of contaminant in the entire vessel was only 10 spores. It says NT is 10. The specific death rate constant for the spore is KD is 6 minute inverse at a given temperature of 121 degrees centigrade. Now you need to find the holding time. What you can assume, there is no death during the heating and cooling cycle. So you have to only consider this is a batch sterilization, and we are only considering the holding time at this moment. So again, it is simple first order kinetics. It will be NT upon N naught equals minus KD into T. All other parameters are given here. So N is 10, NT is 110 to the power 5 into this 150 meter cube is there, that you need to convert into ml and then multiply here. This will be 1.5 into 10 to the power 13 equals kd. Kd is 6 minutes per unit. Kd is 6. You need to find the time. You will get 4.67 minutes. The correct option is B. Next question was, a fermentation process need to be scaled up from 1 liter to 1000 liter while keeping the power to volume ratio constant. So which criteria is being followed? P upon V is constant. A small fermentation is operated at an agitation speed of 250 rpm. If you scale up factor is 10, what should be the agitator speed in the large scale? Now we have to see what criteria is given. The criteria is given as P upon V as constant. It means Ni cube di square is constant. Means N1 cube d1 square equals to N2 cube d2 square. So what you have d1 upon d2 is given, that is 1 by 10. So N2 upon N1 you can find out. And, it will come out to be N2 as N1 into d1 upon d2 to the power 2 by 3. So you'll get correct answer as 53.75 rpm. So it was 54 rpm. Next question is the specification and operational parameters of a laboratory scale fermentation are given: working volume, vessel diameter, agitator speed, ratio of impeller diameter to fermenter diameter 0.45. It is required to scale up this fermenter to 5000 liter, assuming the scale up is performed at a constant impeller tip velocity. Constant impeller tip velocity means N1 D1 equals N2 D2. What is that? And it says the scalar factor corresponds to the cube root of volume ratio. It's fine. What is the required agitation speed in the large fermenter? So these are the given data we have already discussed. The scale-up criteria itself, V2 upon V1 to the power 1 by Q. So the factor scale-up factor is coming out to be 14.8188. So diameter of large scale will be 14.88 or 15 times of the small tank diameter, and correct answer is 30.23. Let me see if there is any query so far. So there is one query we have received. Again, this is how many total number of questions will be there in the final exam. So the duration of final exam will be about 3 hours. It will be in online mode. And if I remember correctly, typically there will be about 50 number of questions. So 50 number is not too much for the 3-hour exam. So I think you should be able to do it and perform quite well in your exam. Going ahead, we can now briefly discuss. We have some time to discuss next week, that is bioprocess instrumentation and control. So in this week, we discussed what are the various measuring devices, particularly sensors for the bioreactors. So what do you want to sense? We discussed, we can sense the physical parameter, chemical parameter, as well as the biological parameters. Then next was measurement of process parameters. What are the various techniques we discuss a few cases like measurement of temperature, measurement of pressure, measurement of dissolved oxygen, measurement of pH, measurement of biomass. Then next we discuss the process control system. What is the necessity of the process control and how the process control works. So we discuss here because once you are having some different monitoring system, it may be the inline, it may be online, it may be the offline monitoring system. So the whole purpose of system is to maintain the desired environmental condition. It will be the temperature, it will be the pH, it will be dissolved oxygen, it will be the nutrient condition. So for that, first you have to measure with time because this is a dynamic system. It keeps changing with time. How these parameters are changing. Then you need to have a set parameter that what is a desired value. Then based on difference of this measured value and the set parameter, it's called the error. And based on that, the process control works to minimize this error. Then next we discuss what is process dynamics because once you have disturbed the equilibrium, it takes some time to reach to a new equilibrium. The time taken during this process of disturbance or some change in the parameter, it follows a certain theoretical or the fundamental process, and those process can be explained with a set of mathematical equations, and those equations can further be solved to get the solution. Then we should have to find out how long it will take to establish a new equilibrium. Then finally, what are different type of controller? We discuss proportional controller. Then proportional can be added with proportional integral controller or proportional derivative controller. Then we can have all three controller together. That is the PID, proportional, integral, and derivative controller. And in addition, we have discussed very simple controller, that is the on-off controller. Now we'll go ahead with a few questions for this week. So it is that during the fermentation, dissolved oxygen is monitored continuously inside bioreactor, but operator manually enters the reading every 10 minutes for records. This represents, so it says there can be three different type of monitoring: inline, online, and offline. So it says in case of inline, the monitor data is directly transferred to the controller. While in the case of online, it is monitored but the manually entered to the controller. And offline, the data is also not monitored online. You have to take out the sample, analyze, then you can enter to the controller. So this is the example of online sensor. It says online sensor. Sensor is connected to the reactor and continuously monitors the parameter in real time, but data processing or recording might be manual or automated. Here, the data is continuously measured, but only periodically noted by the operator. Next question was this. In a bioreactor monitoring system, different parameters are measured to assess the condition of fermentation broth. Some parameters reflect chemical parameters, while other indicates a physical parameter. Which of the following is not a chemical parameter? So we have, as I told, we categorize those monitoring parameters into the physical, chemical, and biological parameters. And here if I see the list, there are oxygen, electric conductivity, redox potential, these are all chemical parameter, while this optical density we consider in the biological parameters. or sometimes this OD can also be considered in the case of physical category as well. But mostly as it indicates the biomass concentration, it is considered as a biological parameter. So A, B, C, all three are the this chemical parameters. Option D is correct. So A is the chemical parameter, B is chemical parameter, C is chemical parameter, D is a physical or biological parameter. In the question number 3, it was in fermentation process, it is important to monitor the temperature of culture broth accurately. Which of the following temperature sensor is commonly used in a bioreactors? Due to its high sensitivity and reliability, so this is based on the metal resistance thermometer, also known as the RTD. So RTD provides highest accuracy, sensitivity, and stability for bioprocess applications. It measures the temperature by controlling the resistance of metal. The metal is typically the platinum with temperature. RTD are also durable and suitable for sterilizable bioprocess environment. So many times we need to sterilize this sensor as well. As you need to measure the pressure. So in bioprocessing, which instrument is most suitable for measuring low pressure? We have discussed high pressure, moderate pressure, and the low pressure in operation like vacuum filtration. So here the manometer, electric resistance pressure gauge, and elastic element based gauge like button tube pressure gauge, they typically measure the high pressure. Only the Pirani gauge can measure the low pressure, particularly the vacuum pressure. So it says for the low pressure measurement less than 1 millibar, we have Pirani gauge listed here. Next question was in bioreactor operation, accurate measurement of liquid and gas flow rate is essential for process control. Which of the following instrument is commonly used for this purpose? We have discussed there could be the flow of liquid as well as the gas, and typically it follows Bernoulli theorem. So for that we have different flow devices, but most common is rotometer, which is applied for the both liquid and gas flow rate measurement. So the first one, this is the venturimeter and this is the rotometer. Next question was, which type of equation is commonly used to model dynamic system? So we can have this algebraic equations, we can have polynomial, but most of the time we end up with differential equations. Next question was, what is the primary function of monitoring the process? Monitoring in bioprocess engineering. So why we want to monitor? Because once you are monitoring, then only you should want to maintain the optimal condition and detect the deviation. And once you are able to detect, some corrective measures can be taken by the manual or automatic controller to maintain the optimal process parameters. The next question was in the feedback control. So we can have feed forward control system and feedback control system. The controllers acts based on, so whatever output stream is going, which we are monitoring, the measured variable, that is also called the control variable. So we are monitoring the control variable. And this is the control variable is now compared with your desired value or the set point, and difference between these two we refer as the error. Yeah, so here you just see this is output we are measuring and we are calling it the control variable because we are going to control this. This goes through this measurement devices and the value is compared with the set point or desired value. Then it goes to the control signal in form, it goes to controller. Then from there, the control signal goes to final control element. Then it does some manipulative variable, like it want to open the valve, it want to increase the flow rate, it want to decrease the flow rate. So whatever action is required, that is performed by the formal control element, and those variables are called the manipulated variable. The next question is, if a system has 6 variables and 4 equations, how many degree of freedom does it have? So what it says, you have to quickly recall the formula for the degree of reduction, which says degree of reduction is number of variables minus number of independent equations. So in this case, the number of variable was given as 6, and there were 4 equations. So we can quickly put the value straightforward and we'll get degree of freedom as. So degree of freedom indicates the minimum number of variables required to define a system or the maximum number of variables that you can fix on your own. So in this case, you should be able to fix any 2 more parameter. And next is related with transfer function. So transfer function is defined as the ratio of outlet to inlet. Here, you need to check the transfer function of a PI control. So PS is the outlet, ES is the error, AC is the gain. So PI, P means this should be 1 here. So it's directly proportional to KC. But in the case of integral, so it should not be tau is, rather it should go 1 upon tau is. So in this way, option B is correct, which defines the transfer function for a PI controller. So that's it. It was all about this chapter 10. So here you just see this is the PI controller. So first contribution is coming from this proportional controller. Then this is a AC upon tau I, that is a integral controller. Next week was related with downstream processing. So there we splitted this downstream part into 2 different modules, week 11 and week 12. Week 12 also includes the bioprocess economics part. So let me see if there is any more queries. So far we have not received any further queries. So what we can do, I can quickly discuss what we have included, we have discussed in the week 12 and week 11. So in the week 11, we discussed first, what is the importance of downstream processing? So what we discussed here, it was particularly in terms of its importance. So once you have produced, so you need to recover, then only you can apply any metabolites or any product. So first, for any given application, we need to recover, we need to purify, we need to first separate, then we need to purify, then only we can go for its application. And second important part is typically we have discussed that downstream processing, it accounts for about more than 50% of the total process cost. So this is very important to select this effective downstream processing. Now further what we discuss, if you keep on increasing number of downstream processing unit operation, then what will happen? Of course, you are going to increase the purity, but at the same time, the yield is going to decrease by adding more number of unit operations or more number of steps. For example, if you are having just one unit with efficiency 9, then overall efficiency will be 0.9 or 90%. But if you are having two units, both are having the separation efficiency of 0.9, then overall efficiency will be 0.9 into 0.9 equals 81%. So if you keep on increasing the number of steps, you are going to compromise with the yield, but at the same time, you are going to increase the purity. So you have to balance between these two. The next question, we discuss various techniques used in the product recovery. So there we started your product, it may be your cells itself, a product may be intracellular product or a product may be extracellular product. So there the first step what you have to do, you have to separate the solids, that is the cells from the broth. So there we discussed filtration and adsorption, sedimentation methods or centrifugation. So mostly the sedimentation and centrifugations are applied for the first step, solid liquid separation. And once it is done, then we go for the product recovery, the purification and so first part is the cell separation and disruption. So there we discuss various mechanical and non-mechanical methods for the cell wall disruption. Then for the first step, how to separate the solid, we discuss the centrifugation, where the driving force is centrifugal force. Filtration, driving force is the pressure gradient, delta P, and sedimentation, the driving force is mass or the gravitational force. So there we had discussed for the product recovery, the extraction, mostly it is solvent extraction and different chromatographic techniques. So based on it includes this mobile phase and stationary phase. Based on nature of the stationary phase, we call the different type of chromatography like affinity chromatography, ion chromatography, gel filtration. And further, if it is operating at very high pressure, then we call it HPLC. So that is most commonly used in the laboratory setup, and also the proprietary HPLC is there for the commercial application. So going ahead, we have some time, so I can quickly go through a few questions of this week's assignment. So the first thing was, in the fermentation industry, producing penicillin, which downstream step is the immediately after fermentation? So as I told, we are going to remove the cells. The first step is the solid liquid separation or the cell removal. Going to the next question, it says in industrial enzyme production, for example, amylase, which is a extracellular, which are the following would be the first major separation after the fermentation. What you have to do, you have to remove the cell to obtain the cell-free supernatant because it is a extracellular product. Third is the concentration of a product before treatment is 5 gram per liter. After downstream processing, the concentration increased to 20. Then what is the concentration factor? So concentration factor is defined as concentration of product after treatment and concentration of product before treatment. It is 20 upon 5 is means 4. The concentration factor is 4. Next question was super coil plasmid DNA for gene therapy application is produced using high yielding recombinant bacteria. And after the cell culture step, the DNA is recovered during a series of 5 different unit operations. The process used and percentage of product recovery for each step is as follows. We started with microfiltration with efficiency of 89%, cell disruption efficiency of 74%, precipitation the efficiency of 71%, ion exchange chromatography efficiency of 82%, and Rangel chromatography separation efficiency of 68%. Now it says what will be the total purification efficiency, and you can see what fraction of plasmid DNA produced by a cell is available at the end of downstream processing. So there are 5 steps. We just multiply all 5. You just see the overall product recovery has decreased significantly to only 26%. The correct option is A. Next question is, that is related with terminal settling velocity for the Newtonian fluid and also in the laminar region. So it says the stroke law, it says the settling velocity is directly proportional to the density difference, proportional to the force or mass, that is G, and proportional to the size of the particle dp square, and inversely proportional to the viscosity because it offers the resistance. The settling velocity inversely proportional to viscosity and directly proportional to change in the density or difference in the density of the particle and fluid, diameter of particle whole square and into G. So how did you derive this equation? So you derive that. So during this gravity settling, there are 3 forces: gravitational force downwards, drag force upwards, and buoyancy force upwards. If you balance this out, so you'll get settling velocity is proportional to dp square, difference in density, gravitational constant, and inversely proportional to the viscosity. Next question was aqueous two-phase extraction system is used to recover lipase from a solution. So here PEG dextran mixture is added and solution separates into the upper phase and the lower phase with a partition coefficient of 3. Now it says the ratio of upper to liquid phase volume is also given 5. You can quickly calculate the enzyme recovery or yield for this case. So if you remember this partitioning coefficient yield, so it is, the formula is yield as K into VU divided by K into VU plus VL. What is the ratio of upper to lower volume is 5. So if you can take this VL as 1, so VU will be 5. And partitioning coefficient is 3, so we'll get yield of 24%. Next question was related with the sedimentation time. So again here all the parameters are given to you. It says sedimentation tank of height 300 centimeter, is used in a conventional activated process to separate the suspension of spherical shaped granules large biomass of 1 millimeter diameter. So diameter is there, viscosity of liquid is 1 centipoise. The difference in density is also given 1 gram per centimeter cube. And if biomass reaches its terminal velocity instantaneously, the biomass settling time will be 1. So first you calculate the terminal settling velocity. It is coming out to be 5.44 centimeter per second. And how much time it will take to travel 300 centimeter? It will be about 55 seconds or 0.92 minutes. The correct option is option A. Next question was based related to chromatography. It says which type of chromatography is more suitable for separating protein based on the molecular size. So, but based on the molecular size, we go with this gel filtration chromatography. Here, the smaller particles enters into the pores of the gel. So they take longer time to come out of the column, while the larger particles are quickly passes through the column. Next question was which chemical mechanism is mainly responsible for disrupting cell by solubilizing membrane lipid? So we can use this detergent. So they solubilize the membrane lipid to disrupt the cells. So you can see surfactant, they solubilize lipid. Alkali, they disrupt the cell wall by saponification of liquid. Organic solvent, they penetrate and swell cell wall lipid. Then enzymes, you can use this specific enzyme to digest the cell wall. For example, this lysozyme degrades the cell wall. Next question was based on the efficiency factor in the cell disruption, what is the key drawback of applying too many disruption cycles or process? So when we go for more and more number of disruption cycle or process, one option is you end up with fine debris also. And that once it is too fine, its mass also accordingly decreases and it becomes difficult to separate those debris. So it says the correct option is formation of fine debris makes clarification difficult. Yeah, so week 12 was again the continuation of product recovery, and also we discussed this bioprocess economics. So in this week, what we discussed was some of the part, particularly this adsorption separation process, which was not covered in the last week, that was discussed here. In the downstream processing, and in addition, we also discussed in the last lecture was related with bioprocess economics, because some sense of this monetary part, once someone is setting up a process, then what is the turnover number, what is the rate of return. So those simple concepts along with some examples were discussed in the product recovery. Along with adsorption, we also discussed the membrane separation and drying. So here, earlier in the first step, solid liquid separation, we discussed the conventional filtration process. But here we discussed the membrane filtration purely based on the size of the pore, particularly microfiltration, nanofiltration, ultrafiltration, and reverse osmosis. The driving force is the difference in the pressure. And depending on the pressure and force size, you can separate small ions, or again you can go with in the reverse osmosis. You can separate thus even the soluble ions which are present in the water. And in case of drying, also we discussed that what is the drying rate curve. So it is starting with the initial heating period, then constant rate period, then first falling, and then second falling. There we discussed two concepts. First is the critical moisture content. The critical moisture content comes at the end of first constant rate period. So there we say that at the critical moisture content, whatever uh, moisture was there at the surface, that is being removed now. Now next comes the internal moisture that comes out during the first falling period and second falling period. And at the end, again, we reach to the equilibrium moisture content. It means now whatever moisture is there, that cannot be removed by the drying process. So with this, let me see if there is any other query or the comment. So if there is no query here, so once again, I thank to all the participants for and students for registering this course, and I hope this course has been very much useful for your academics, for clearing different concepts for these working professionals. So thank you so much. With this, all the best for the participant who will be appearing for the online exam, which is scheduled to be held next month. Thank you. Thank you so much.